In this section, I'm going to discuss two other concepts of differentiability called Gato differentiability and share differentiability. Then I'm going to discuss their relation with directional differentiability, and I also prove a subdifferential characterization for differentiability. Okay, so let me start the section by the definition of Gato differentiability. Let f from Rn to the extended real line be a function, and let x bar be a point in the interior of the domain of the function. We say that f is Gato differentiable at x bar if there exists an element v in Rn such that the limit lim as t approaches 0 of f of x bar plus t times d minus f of x bar minus t times the inner product of v and d over t is equal to 0 for all d in Rn. Okay, so in this definition, f is not necessarily convex. In addition, this limit is computed as t approaches 0. As we see from the previous section, in the definition of directional differentiability, we require the limit as t approaches 0 from the right. Okay. Now, in this situation, we can see that the inner product of v and d is equal to the limit of f of x bar plus t times d minus f of x bar over t as t approaches 0. Okay, if f is differentiable at x bar, and we can show that the element v that satisfies this definition is unique. Okay, and it is called the Gato derivative of the function f at x bar. Okay, so if f is Gato differentiable at x bar, as above, the element v is unique and is called the Gato derivative of f at x bar, denoted by okay. So now, if f is Gato differentiable at x bar, then from the definition, we will see that the inner product of the Gato derivative of f at x bar and d is equal to this limit. Okay, so in the next proposition, I'm gonna establish the relation between the Gato differentiability and the directional differentiability. let f from Rn to the extended real line be a function, and let x bar be in the interior of the domain of the function. Then f is Gateau differentiable at x bar with its Gateau derivative v, if and only if the directional derivative of f at x bar in the direction d exists, and it is linear with respect to d by this formula for all d in Rn. Okay. So let me go ahead and give the detailed proof of this proposition. Let me first prove the implication. Suppose that f is differentiable, f is Gateau differentiable at x bar with its Gateau derivative v. Then let us show that the directional derivative of f at x bar in any direction d is given by this formula. Okay, so by the definition, of Gateau differentiability, the inner product of v and d is equal to the limit of f of x bar plus t times d minus f of x bar over t as t approaches 0, and this is true for all d in Rn. Okay, and therefore the limit as t approaches 0 from the right is also equal to the inner product of v and d. Then the inner product of v and d is equal to the limit as t approaches 0 from the right of f of x bar plus t times d minus f of x bar over t. And this is true for all d in Rn. Okay. So from here we see that by the definition of the directional derivative, we get that f prime of x bar in the direction d exists for all d in Rn, and in addition it is given by this formula is equal to the inner product of v and d. Okay, therefore we have completed the proof of the implication in this proposition. Now let me go ahead and give the proof of the converse. For the converse, suppose that f prime x bar d exists and is equal to the inner product of v and d for all d in Rn. Let us show that f is Gateau differentiable at x bar and v is its Gateau derivative. Okay, so from here we see that the directional derivative of f at x bar in the direction minus d is also equals to the inner product of v and minus d for all d in Rn, because minus d is also an element of Rn. Okay, from here we get that minus of the directional derivative of f at x bar in the direction minus d is equal to the inner product of v and d. And this is actually the left directional derivative of f at x bar in the direction d. Okay, so from here we have the following equality. The limit of f of x bar plus t times d minus f of x bar over t as t approaches 0 from the right is equal to the inner product of v and d. Okay, this is true because of this equality. Okay, on the left we have the directional derivative of f at x bar in the direction d, and at the same time, because the left directional derivative of f at x bar in the direction d is also equal to this, by the definition we have that the limit as t approaches 0 from the left of f of x bar plus t times d minus f of x bar over t is also equals to the inner product of v and d. And this is true for all d in Rn. Okay? Combining this equality and this equality, we see that the limit as t approaches 0 of f of x bar plus t times d minus f of x bar over t is equal to 0 is equal to actually the inner product of v and d for all d in Rn. Okay, so by the definition of Gato differentiability, we get the required result. That is, therefore, f prime is equal to v. Okay, so f is Gato differentiable at x bar because this limit is exists and is equal to v times d, and moreover its Gato derivative at x bar is exactly v. So the proof of the theorem of the proposition is complete. Now I'm going to give the definition of another concept of differentiability called Fisher differentiability. Let f from Rn to the extended real line be a function, and let x bar be a point in the interior of the domain of the function. We say that f is Fisher differentiable at x bar if there exists an element v in Rn such that the limit as h approaches 0 of f of x bar plus h minus f of x bar minus the inner product of v and h over the Euclidean norm of h is equal to 0. Okay, over here note that h is in Rn. And we can also show that the element V that satisfies this definition is unique, and this is called the Fisher derivative of f at x bar. The element V is called the Fisher derivative of f at x bar and is denoted by f prime of x bar. Okay, next I'm going to show that for a convex function, the Gateau differentiability coincides with the Fisher differentiability. That is a very, very nice property of convex function, and this is not true in general. That means we can find a counterexample for a non-convex function where the function is Gateau differentiable at a point x bar, but it's not Fisher differentiable at x bar. Now I'm going to discuss the relation between Gateau differentiability and Fisher differentiability. Let f from Rn to the extended real line be a function, and let x bar be a point in the interior of the domain of the function. Okay. If f is Fisher differentiable at x bar, then it is Gateau differentiable at this point. And the converse is satisfied if f is a convex function. The converse also holds if f is convex. Okay, now let me give the proof of this theorem. Suppose that f is Fisher differentiable at x bar. Now we can let v by its derivative at x bar. Okay? By the definition, the limit as h approaches 0 of f of x bar plus h minus f of x bar minus the inner product of v and h over norm of h is equal to 0. Okay? Let us now show that f is Gateau differentiable at x bar with the same Gateau derivative v. How come this is true? For fix any d in Rn, we have that the limit of f of x bar plus t times d minus f of x bar minus t times the inner product of v and d over t as t approaches 0 is equal to this. f of x bar plus t times d minus f of x bar minus v, the inner product of v and t times d over the t times norm of d, and then here we multiply by norm of d. So observe that t times d here is exactly x bar plus t times d minus x bar. Okay, so t times d here plays the role of h in this definition. Okay, and here we look at the case where d is not 0. Okay, so that we can divide. Okay, and because this limit is equal to 0, and over here for h to be t times d, norm of h is t times norm of d. Okay, is the absolute value of t times norm of d, and this is this goes to 0 as t approaches 0. Therefore, this limit is equal to 0. Okay. Therefore, and obviously this is true. This limit is also 0 if d is equal to 0. Therefore, f is Gato differentiable at x bar. With Gato derivative v, which is the same as the Fisher derivative at x bar. Okay, so now I'm going to show that the converse is true under the complexity of f. Now let me go ahead and give the proof of the opposite implication. So suppose that f is Gato differentiable at x bar. Our goal is to show that it's Fisher differentiable at this point. So let v be the Gato derivative of the function f at x bar. Then, by the definition, we have that the limit of f of x bar plus t times d minus f of x bar minus t times the inner product of v and d over t as t approaches 0 is equal to 0. And this is true for all d in Rn. Now, we will show that the limit of f of x bar plus h minus f of x bar minus the inner product of v and h over the norm of h as h approaches 0 is equal to 0. Okay, if we can prove this, then our conclusion is f is Fisher differentiable at x bar and its derivative is v, which is the same as the Gato derivative of the function f at x bar. Now, let us prove this by a contradiction argument. So, we use star to denote this limit equality. So, by contradiction, Suppose that star is not satisfied. Then, if we use the definition of limit, we will see that then there exists a positive number epsilon naught greater than 0 and a sequence hk in Rn not converges to 0. Over here, hk is non-zero for all k, such that the absolute value of f of x bar plus hk minus f of x bar minus the inner product of v and hk over norm of hk is always greater than or equal to epsilon naught, and this is true for all k in Rn. I'm sorry, for all k in n. Okay, for all positive integer k. Now, let us define tk by the norm of hk. Okay, and as we know, tk is a positive number for every k, and tk converges to 0 as k approaches infinity. Okay, we also let dk by hk over norm of hk. So from this, we will see that norm of dk is always 1 for all k. Okay, and therefore dk is a bounded sequence in Rn. And as we know, any bounded sequence has a convergent subsequence in Rn. So we can say, by working with not subsequence, we can say that without loss of generality, we can assume that dk converges to an element d in Rn as k approaches infinity without loss of generality. Suppose that dk converges to an element d in Rn, and from this we will see that norm of d is equal to 1. Okay, now from here we will try to come up with a contradiction. Using these notations, we are going to rewrite this inequality as follows. We have that epsilon naught is less than or equal to the absolute value of f of x bar plus hk minus f of x bar minus the inner product of v and hk. Everything is divided by norm of hk. Okay, so this is equal to the absolute value of f of x bar plus norm of hk times hk over norm of hk. So this is still hk because we can simplify norm of hk minus f of x bar. And similarly, this is the inner product of v and norm of hk times hk over norm of hk. And everything is divided by norm of hk. So this is equal to the absolute value of f of x bar plus we replace this by tk and we replace this by dk. So we have this f of x bar plus tk times dk minus f of x bar minus the inner product of v and tk times dk. Here everything is divided by norm of hk, which is tk. Okay, and we rewrite this expression as follows. This is the absolute value of f of x bar plus tk times dk. So we will subtract a new term, which is f of x bar plus tk times d, and then after we subtract this new term, we add this new term to make sure that the expression remains the same. So we add f of x bar plus tk times d. Okay. And now we subtract f of x bar, so we keep f of x bar the same here. Now here we subtract the inner product of v and tk times dk. So over here we're gonna add a new term, which is the inner product of v and tk times d. Okay. So after we add this new term, we subtract that new term again to make sure that the expression remains the same. Okay, and everything is divided by tk. Okay. Now we are going to use the triangle inequality to obtain the following. So this is less than or equal to the absolute value of f of x bar plus tk times dk minus f of x bar plus tk times d, and everything is divided by tk. Okay. Now we add another fraction. So in this fraction, I'm going to group this term, and the last term here together. Okay. So it will be the absolute value of f of x bar plus tk times d minus f of x bar minus, for the last term here, we can take tk out of the inner product notation. So we subtract tk times the inner product of v and d. Okay, and everything is divided by tk. Now in this expression there are still two terms here, so we add this to the sum. So here we have v, the inner product of v and tk times d. Here we subtract v and the inner product of tk times dk. So we can rewrite this as the inner product of v, this is tk times d, and we subtract the inner product of v, and over here we have tk times dk. And again, everything is divided by tk. To continue the proof, we are going to use a very important property of convex functions. That is, if x bar is a point in the interior of the domain of a convex function, then f is locally Lipschitz continuous at x bar. Okay? So, because x bar is in the interior of the domain of the function f. F is locally Lipschitz continuous. At x bar. Thus, there exists L greater than or equal to 0 and delta greater than 0 such that the absolute value of f of x minus f of u is less than or equal to L times norm of x minus u. And this is true for all x and u in the ball with center at x bar and radius delta. Okay. Now, from here, we will apply the Lipschitz continuity of the function f in this situation, because when k is sufficiently large, this term x bar plus tk times d, this element will be in the ball with center at x bar and radius delta, because it converges to x bar as k goes to infinity. And similarly, here x bar plus tk times d will be in this ball when k is sufficiently large. Okay, so then we get this epsilon naught is less than or equal to, okay, so it's less than or equal to L times norm of x bar plus tk times d minus here actually it's dk, okay, minus x bar plus tk times d. Everything is divided by tk. Okay, so we already applied this inequality where x is equal to x bar plus tk times d and u is equal to x bar plus tk times d. Okay, therefore this is less than or equal to L times norm of x minus u, which is this minus this. Okay, and then we keep the second expression in this inequality the same. So this is the absolute value of f of x bar plus tk times d minus f of x bar minus tk times the inner product of v and d. Everything is divided by tk. Okay, for the last one here, we realize that this can be written as tk times the absolute value of the inner product of v and d minus dk, and everything is divided by tk. Okay, now finally we can get this. This is always less than or equal to. Here we can simplify x bar, okay, and then we can also simplify tk and get L times norm of dk minus d. Okay, and then we keep the second expression the same. This is f of x bar plus tk times d minus f of x bar minus tk times the inner product of v and d. Everything here is divided by tk. Okay, now here we will use the Cauchy-Schwarz inequality after simplifying tk and get norm of v times norm of d minus dk. Okay. As we know, dk converges to d, so this converges to 0. And similarly, this converges to 0 as well. Okay. Now, we use the fact that f is Gatto differentiable at x bar with Gatto derivative v. So for any sequence tk that converges to 0, f of x bar plus tk times d minus f of x bar minus tk times the inner product of v and d over tk converges to 0 as k approaches infinity. So this expression also converges to 0 as k converges to infinity because tk here converges to 0. Okay. So this sequence, the sum of three sequences, converges to 0 as k approaches infinity. And here epsilon naught is a positive real number, so we have arrived at a contradiction. So this is a contradiction. Okay, so this contradiction shows that the expression stars must be satisfied. And what is the expression star? Let me recall it. So this contradiction shows that this limit is equal to 0. And therefore, f is Fisher differentiable at x bar. Therefore, the Fisher derivative of f at x bar is v, which is also the same as the Gatto derivative of the function f at x bar. So the proof is complete. Okay. So in this proof, we use a very important property of convex function. That is, if f is a convex function, then it is locally elliptic continuous at every point in the interior of the domain of the function. Okay. So one important remark: if this is also true for non-convex function, but we have to assume the local elliptic continuity of the function f at x bar. Then we can still arrive at the same conclusion, that is, Gatto differentiability of f at x bar is equivalent to the Fisher differentiability of the function f at x bar.